All right, so we have this block. It's not drawn to scale in this figure. We want to calculate a couple things. So first of all, just looking at the picture, I think you can kind of predict what this is about. The spring's going to compress, the block will get released, it'll go up the ramp. And we want the speed of the block when it leaves the spring. So let's start with all this spring energy getting converted into kinetic energy. Now the reason I know to use 1/2 kx squared is that it is an ideal spring, and that implies that it's 1/2 kx squared, a Hooke's law spring. The halves cancel. And when we actually calculate the speed, we isolate, that's going to be square root of k over m times x. And when we work that out, that is actually going to give us a v of 2.29 meters per second. All right, now we want the maximum distance d that the block travels up the ramp. Let's do a little modification here. Let's actually talk about the height. Okay, so this is height. This angle is 20 degrees. And from SOHCAHTOA, we know that sine of 20 is h over d. So h is going to equal d times the sine of 20. Keeping that in mind to get the distance d that travels up the ramp, well, here's the interesting thing. Since it's a frictionless surface, energy is not dissipated at all. So I can actually directly convert the spring energy into gravitational energy. So I'm just going to isolate d here, so that'll be kx squared over 2mg sine theta. That's what d is going to be, and when we plug that in, we're going to end up getting that d equals 0.767 meters. I'm using here g is 10, by the way. Now for this last part. Let me do the easy parts of this graph first. So this is where we have the spring expanding. This is where it's the flat part, and this is where we go up the ramp. So let's be clear. During the flat part of the journey, there's no net force on the block, so it travels at a constant velocity. And then as it goes up the ramp, it's got uniform acceleration, so it slows down uniformly. Now, as the spring expands, let's be clear. Here, it's a Hooke's law spring expansion. So this isn't a nice, neat, linear increase in speed. What's actually happening is you have the maximum force when the spring is compressed. And then as the spring expands out, the speed, the rate at which it gains speed gets slower and slower, or less and less, because there's less net force on it. So it's actually going to be kind of a leveling off like this. Okay. Another way to think about it is if you remember Hooke's law, if you have x versus t for a spring, it's a cosine for the position, and for the velocity, it's a sine wave. So you get a little bit part of that sine wave speed right there as it expands. All right, in a second experiment, we have a block placed on the ramp, and they collide. So we want to calculate the speed of the blocks after the collision, before and after. So it says calculate the speed of the two blocks immediately after the collision. So first of all, let's just get VA before the collision. So VA before the collision. First, so let's just be clear. It's released with a speed equal to we got that as square root of k over m times x. Now, the thing is, it goes d over 2 up the ramp, right? So let's just be absolutely clear on what its speed is when it goes halfway up that ramp. And so rather than using this value here, so this is not useful. So halfway up the ramp. So let's be clear. If this is h, and I'm going to call that h nu, we know that h nu is going to equal d over 2 times the sine of theta. And so let's get the speed halfway up the ramp. So we have 1/2 kx squared, and that's going to equal 1/2 mv of a squared plus m times g times d over 2 times the sine of theta. Now let's do a little bit of simplification. We're getting halves to cancel, which is nice. And we're going to get kx squared minus mgd sine theta all over m under a square root. That's going to equal VA before the collision. So that's VA initial. And when we go ahead and actually solve that, we will end up getting 1.60 meters per second. And here I'm using g as 10, so that's 1.60. Now, block B, let's get V of block B before the collision. Okay, so what's going to happen there is it's going to fall mg d over 2. So it has mg d over 2 sine theta is the amount that it falls as far as its height goes, and that gets converted to 1/2 mvb squared. All right. So that means VB equals the square root of G times D times the sine of theta. Continuing, when we put in our numbers, and let's just make sure I have a value for D that's correct. So we are told that D is equal to, all right, so did they give us a value? So D is, we have it right here, 0.767. We solved for that right here. So that's what we'll use. So we will then end up getting, and let me make absolutely sure I have this right. Is it 0.767? It is 0.767 if we are using G is equal to 10. So when we put in our numbers here, for VB, we're going to get the square root of 10 times 0.767 times the sine of 20, and that's how we end up getting VB equals 1.64. And let me just double check. So VA is going to equal 1.60. VB is going to equal 1.64. And so let's go ahead and calculate the speeds after the collision. So we have MAVA plus MBVB. Now, they collide and stick, so that's going to be MA plus MB times their combined speed. So let's just make sure we've got our numbers right. MA is 3, VA is 1.6, MB is 0.5. It's going the opposite way, so let's be careful. That's negative 1.64 because it's going the opposite way as the A block is going. Okay. Direction matters. Okay, so let's be clear. B is going in the negative direction, A is going in the positive direction. We should actually label that here, just so that we're clear. Over 3.5 is V final, and that's how we're going to end up getting about 1.14. Finally, in what direction, if any, are the blocks moving after the collision? Since the number we got is a positive number, that means they're going to move up the ramp, since this is the positive number. And the magnitude of the impulse exerted on block A by block B. That's just going to be J is MV final minus V initial. So that's going to be M times B. So we're going to end up taking 1.14 minus negative 1.62. Make sure, absolutely sure that I have that right. So block B is 0.5. Block A is 3. That's the mass. So going back here, it seems to me that 1.14 is up the ramp and that B speed is down the ramp. I'm a little suspicious. So here we have, let's just be sure. Oh, we want the magnitude of the impulse exerted on block A by block B. Let's do that again. Sorry. So it's the impulse on A that we're looking for. Okay, so the impulse on A, by the way, B and A should give you the same number from Newton's third law, but let's just be careful. So the impulse on A is going to be M times A times the final speed, which is 1.14. So that's 1.14 minus 1.60. And our impulse is roughly going to work out to, I'm just going to round it a little bit and just say I'll round it to 1.4 Newton seconds. Now the direction of the impulse on block A by block B, that's going to actually be down the ramp since it slows A down. All right, so that takes care of problem number 2.